Hi, welcome to YouWillUnderstandMath.com. Today you will understand the geometric definition of the limit. In a previous video, I explained why we need limits. One of the reasons we use limits is when we want to know what's going on with the function as we get arbitrarily close to a value. In particular, as we get close to a value which gives us an undefined value for our function. If you take a look at these functions, f of x equals x plus 1. The inputs will be the x values. These will be inputs. The outputs will be the y values, or the values that we get when we plug the x values into f of x. These will be outputs. If x equals negative 1, we plug negative 1 into our function so that we'll have negative 1 plus 1, which is what I have here, equals 0. And so on and so forth for the other values. We get all of these values. Suppose we have f of x equals x plus 1 again, but this time I have some intermediate values for the inputs. Once again, these are our inputs, these are our outputs. If 0 is the x value or the input, then we get 1. If 1/2 is an input, we plug this into our function to get 1/2, and so on and so forth. Now suppose f of x equals x squared minus 1 over x minus 1. This time, if I plug in these inputs, notice what happens when x equals 1. If you plug in 1 here, we have 1 minus 1, which is 0. We have 0 in the denominator, so this function is undefined. You may be thinking, well, we can reduce this and factor out the top so that we have x minus 1 times x plus 1 all over x minus 1. And then you would think we could cancel the x minus 1 factor so that we have x plus 1. Well, the problem is we can't necessarily use cancellation in this case because we need all of the values of f of x. We have to include every single value. We can't throw anything out. However, if we were to use a limit, then we could include the value 1 because limits do not ask us or require us to give the value of the function at a certain point, but it asks us to give the value of the function near a certain point. Notice here I've rewritten f of x equals x squared minus 1 all over x minus 1. What the limit does is the limit looks at the inputs that get closer and closer to the value of concern. In our case, the value of concern is x equals 1, or when the input is 1, because that's where the function is undefined. We have values to the left of 1 here, 0.95, 0.97, 0.99. Notice this sliver of a number line where 1 is the star of the show. To the left of 1, we have 0.95, 0.97, 0.99. To the right of 1, we have 1.01, 1.03, and so on and so forth, which are here. Notice the outputs. When we plug in these inputs, we get these outputs. For example, if you plug in 0.95, you would have 0.95 squared minus 1 all over 0.95 minus 1, and you would get 1.95. Notice what happens here between 0.99 and 1.01. The values from the left are approaching 2. The values from the right are also approaching 2. Therefore, the limit as x approaches 1, because notice that the inputs are approaching 1, so x is approaching 1, then these values, when you plug in the inputs, the outputs are approaching 2. Therefore, the limit of x squared minus 1 all over x minus 1 as x approaches 1 is 2. In fact, we can use the cancellation property here when we're using the limit, but we can't use it when we're just looking at the function. That's another advantage of limits. Because I can cancel, I can write the limit as x approaches 1 of x squared minus 1 all over x minus 1. as a product of its factors, x squared minus 1 is the same as x minus 1 times x plus 1. Canceling the x minus 1 values, I will have x plus 1. The limit as x approaches 1 of x plus 1 means that I would basically be substituting 1 for the x value, which is 2. In the next video, I will show you how the previous problem relates to this definition for the geometric definition of the limit. Thank you for watching. Please like and or subscribe if you've enjoyed this video.